Welcome to the boardroom. Grab a seat. Today, we're not just treating your Cambridge mathematics exam as another standard test. No, we are treating it as a high-stakes, professional corporate pitch. In this scenario, you are the lead analyst. The examiner, well, they are your incredibly demanding board of directors. And let me tell you, every single mark you're trying to secure requires absolute bulletproof justification, precise data extraction, and a totally flawless analytical strategy. We are diving right into an exclusive, behind-the-scenes look at the examiner's playbook to demystify one of the absolute trickiest areas in the entire Cambridge AS and A-level mathematics 9709 syllabus, forces and equilibrium. Now look, if you've already crushed the foundational concepts in syllabuses like 0580, 0606, 4024, 4037, or even 4040, you might be sitting there thinking you are totally ready for this. But trust me on this, the 9709 syllabus demands a completely different level of analytical rigor. It's a whole new ballgame. We are going to break down exactly how you need to pitch your mathematical arguments to the examiner so you can guarantee you extract every single possible method mark available.
What is really fascinating to me about this examiner quote is that the senior grading officials fully, openly acknowledge just how much candidates struggle with multi-stage analysis here. Securing those method marks in this specific friction topic is literally where dreams of an A-star either happen or completely fall apart. To understand why, let me introduce you to two completely typical students we see taking this paper every single year. First up, we've got Alex. Now, Alex is essentially a walking textbook. Alex knows every formula by heart. But when faced with an inclined plane question, Alex just overloads the page with raw mathematical facts. Alex instantly writes down F equals mu r without actually checking the context of the physical situation, providing absolutely zero analysis of whether the particle is actually on the verge of moving. It's just fact dumping. Then, on the other extreme, we have Sam. Sam is constantly stressed, rushing against the clock, completely missing the specific command word requirements in the prompt, and basically just throwing random numbers into a calculator, hoping the final answer somehow matches the marking scheme. You know what happens to both of them? Their exam papers come back completely covered in brutal red pen marks. Why? Because the examiner board isn't just looking for a lucky final number. They are actively hunting for a justified, highly logical argument. You have to prove why you are doing what you are doing. And that's exactly what we are going to fix today.
So, to transform all those nasty red marks into beautiful, confident green check marks, we've put together a completely structured game plan for this explainer. First, we'll tackle the friction challenge head-on. Second, we're defining core principles so your foundation is rock solid. Third, we'll build out the procedural framework. This is your actual step-by-step exam strategy. And finally, we'll reveal the top examiner warnings so you don't step on any hidden landmines.
Okay, Section 1. Let's start with the foundational principles and look closely at why the theoretical architecture of this specific topic trips up so many incredibly smart students. You see, the jump from foundational mathematics to 9709 forces and equilibrium is massive. It requires you to totally shift your mindset. You are no longer just solving for some abstract X. You're modeling actual physical realities. When you break down the assessment objectives for this syllabus, they are targeting very distinct cognitive domains. They want to see your knowledge and understanding, your practical application, and most importantly, your deep critical analysis. The ultimate friction challenge is that candidates mistakenly treat friction like a static, unchanging constant, but it isn't. Friction is a reactive force. Think of it like a lazy force. It only does exactly as much work as it absolutely has to, up to a very specific breaking point. It only reaches its maximum value under incredibly specific critical conditions. This is exactly where the boardroom pitch falls apart for students like Alex, who completely fail to justify their starting equations and just assume friction is maxed out all the time.
That brings us to the most crucial point of this entire explainer. This topic rests entirely on precise definitions and causal relationships. You absolutely cannot just memorize formulas and expect to pass. You have to fundamentally understand the state of limiting equilibrium. So, what is limiting equilibrium? It means a particle is on the exact precise verge of moving. It is the absolute physical tipping point. If a question tells you a block is just sitting there, stationary, friction could be anything up to its maximum. It's an inequality, right? But the very second the command word implies the block is on the point of slipping, boom! That is your explicit, written permission from the examiner to bust out the equation F equals mu r. If you try to use that equation without the object actually being in a state of limiting equilibrium, your pitch to the board is instantly rejected. You literally lose the method marks on line 1 because your causal relationship is completely flawed. You're answering a question they didn't ask. Understanding that difference perfectly illustrates how the Cambridge assessment framework prioritizes analytical depth over just memorizing stuff.
Average candidates, kind of like our friend Sam, go for superficial breadth. They try to do way too many mathematical operations at once without logically structuring their thoughts. Top-scoring candidates, the ones pulling the A stars, utilize a system we like to call the Peel framework. Now, if you take essay subjects, you've probably heard of Peel. Point, evidence, explanation, link. But guess what? It is an absolute secret weapon in advanced mathematics too. Here's how it works for math. Point, you state your physical assumption, like writing down resolving forces parallel to the plane. Evidence, you extract the data, stating friction acts upwards because motion is pending downwards. Explanation, you set up your resolved equation clearly so the examiner can read it like a sentence. Link, you solve that specific equation to answer the exact command word. The principal examiner reports heavily highlight that students who structure their answers this logically achieve significantly higher marks. Before we continue, subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
All right, let's move right into Section 2, the procedural framework. This is the strategy that practically guarantees you're going to hit those strict academic benchmarks and secure every single possible method mark. We are going to take the chaotic, red-inked papers from Alex and Sam, and we're going to transform them into flawless, green-checked boardroom bitches. This is where we take the chaotic, high-pressure environment of the exam hall and impose a totally rigid, foolproof system over it. By systematically following this specific 5-step sequence, you are showing the examiner exactly how your brain works. You're showing them how you identify key elements and execute your analysis with crystal clear working. Step 1. Deconstruct the command word. Are they asking you to show that, calculate, or determine? Because each of those requires a totally different level of written justification. Step 2. Extract the data and, I cannot stress this enough, draw a large, clear force diagram. Step 3. Select your analytical framework. Ask yourself, are we resolving horizontally and vertically here, or does it make more sense to resolve parallel and perpendicular to an inclined plane? Step 4. Execute the analysis using that mathematical Peel structure we just talked about. And finally, Step 5. Verify your answer actually makes physical sense and present it with the correct significant figures. This 5-step process isn't just a suggestion, it is the exact blueprint that the top 1% of students use to consistently score full marks.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Okay, welcome to the interactive workshop segment of this explainer. Extracting data from exam texts and tables requires you to actively interpret relationships. You're not just reading numbers, you're looking for evidence-based conclusions to feed into your framework. Imagine we're looking at a complex data table right now, representing different coefficients of friction across various inclined planes. I want you to imagine a 60-second visual countdown timer has just started. Your challenge, as the lead analyst, is to scan this data and pull out the core trend. Tick-tock. Look at the relationship between the angle of inclination, the normal reaction force, and the required frictional force to maintain equilibrium. We're 20 seconds in. If you just look at the numbers blindly, you are totally going to miss the physical reality. 40 seconds. Think about it. As the angle increases, what happens to the normal reaction? It decreases, which means your maximum available friction, your μr, is actually dropping at the exact same time the gravitational pull down the slope is increasing. Time's up. Spotting that relationship instantly in the first 60 seconds of reading a prompt gives you an intuitive, built-in check on whether your calculations are actually right later on. Let's shift our focus to critical analysis and exactly how examiners award those precious method marks based on your ability to evaluate the problem. Listen to me carefully. Method marks are the absolute lifeblood of the 9709 syllabus. Let's say you do all the math perfectly, but at the very end, your finger slips, you punch the wrong number into your calculator, and your final answer is wrong. You lose the final accuracy mark. But if you have a perfectly structured, logically sound method written down, you will still earn the vast majority of the credit for that question. The examiner desperately wants to see your brain on the paper. They want to see that you understand the fundamental mechanics of the universe, not just that you know how to operate a piece of plastic with buttons on it.
Top-scoring candidates constantly evaluate evidence. They explicitly identify limitations, they note the assumptions they are making, and they explain how those affect the final conclusions. All right, it is time for Challenge 2, Find the Flaw. I am going to read a deeply flawed sample paragraph from Sam's actual exam paper. Listen closely. Sam wrote, "Since the block is resting on the plane, F equals μr. Resolving vertically gives R equals mg cos theta. Therefore, friction is 0.5 times mg cos theta. I'm putting 30 seconds on the clock. Your job is to identify the exact sentence that is hemorrhaging marks. 15 seconds left. Are you looking at the first sentence? Time's up. Did you spot it? The fatal flaw is Sam's very first assumption. Since the block is resting on the plane, F equals mu r. Resting does absolutely not mean limiting equilibrium. The friction could be far, far less than the theoretical maximum. Sam just threw away almost all the method marks for the entire question by making a completely unjustified physical assumption right out of the gate.
To avoid Sam's fate, you must employ this loop: deconstruct, solve systematically, and evaluate reasonableness. Break the given info into logical steps. Okay, challenge 3, speed writing. You have a 30-second timer to mentally map out one perfect Peel paragraph for resolving forces parallel to a slope where a particle is on the point of slipping upwards. Ready? Go. Start with your point. Say to yourself, assume limiting equilibrium as motion is pending upwards. Now your evidence. Therefore, friction F acts downwards, perfectly parallel to the slope. 15 seconds. Now the explanation, resolving parallel. The driving force must equal friction plus the weight component, mg sine theta. And finally, your link. Substitute F equals mu r to find the driving force. Time. If you can systematically loop through that exact mental process under the intense pressure of the exam clock, your mark potential literally jumps from 0 to 100%.
Let's move into Section 4, Top Examiner Warnings. We are going to look at the actual principal examiner reports to uncover the critical, grade-killing mistakes you absolutely need to avoid. We are taking this data straight from the boardroom, straight from the people who actually grade your papers, to ensure you sidestep the most common errors that tank candidates every single testing series. The data shows the top 3 traps students fall into are 1. Using the wrong approach for the context, 2. Failing to evaluate their presentation format, and 3. Giving generic rather than specific answers. Let's break these down so you don't do them. Trap 1. Wrong approach. This usually looks like a student applying static equilibrium formulas to a dynamics problem where a particle is clearly accelerating. Huge mistake. Trap 2. Format and presentation. Look, if your force diagram is a tiny, messy, smeared scribble crammed into the margin of the page, the examiner cannot follow your resolved components. You need to draw large, clear diagrams with big arrows indicating the positive direction. Trap 3. Generic answers. If the exam prompt asks you about a specific steel crate on a specific wooden ramp, your final concluding sentence must reference that crate and that ramp. It has to perfectly address the exact command word used in the prompt, not just spit out a number.
This next one is a massive warning directly from the source. It says, always clearly define your terminology before applying it. If you want to secure those professional skills marks, you have to communicate clearly. If you decide to use a variable like T for tension or R for normal reaction in your math, you better ensure it is clearly labeled on your diagram. Examiners explicitly note that candidates who just throw unassigned, random variables into their equations are essentially asking the grading board to guess what they mean. Think about our boardroom pitch analogy. You would never stand up in front of a CEO and show them a chart without labeling the axes, right? So do not hand an examiner an equation without defining your physical terms. This one simple, tiny act of clarity automatically elevates you from a mid-tier candidate to a top-tier analyst in the eyes of the person grading your paper.
To ensure you never, ever miss a step in the heat and stress of the exam room, we've created a custom acronym for the factors affecting friction and limiting equilibrium. It's a quick memory hack. The acronym is FLED. FLED. Let's lock this in. F stands for force diagram. Draw it big, draw it clear. L stands for limiting state. Stop and ask yourself, is the object actually on the point of slipping, or is it just resting peacefully? E stands for equations. Methodically set up your resolved components perpendicular and parallel to the plane. And D stands for direction. Always double-check that your friction arrow is pointing in the exact opposite direction of the intended motion. If you mentally run through FLED every single time you see a friction question, you systematically eliminate the careless, easily avoidable errors that cost students precious grade boundaries.
All right, we have reached the final review. Let's bring all of this high-level strategy together and review our core methodologies. We've journeyed through the theoretical foundations of friction, we've exposed the common pitfalls by looking at Alex and Sam's disastrous mistakes, and we've built a bulletproof procedural framework to replace that chaos. Now it's time to lock in the final system that guarantees top marks.
Your path to total mastery requires integrating clear definitions, strictly following the procedural sequence, and always checking your systematic problem solving to see if the physics actually makes sense. We've condensed everything from this explainer into 3 golden rules you cannot break. Rule 1.
Command word decoding. Never start writing until you know exactly what the verb in the prompt is demanding of you. Rule 2. Peel framework application. Structure your mathematical working with a clear point, evidence, explanation, and link. Make it a logical, undeniable argument. Rule 3. The time management matrix. Don't spend 10 minutes agonizing over a simple 2-mark definition question, and definitely don't rush through an 8-mark multi-stage equilibrium analysis. Allocate your time strictly based on the mark weighting provided on the paper.
I want you to ask yourself right now, seriously, how can you integrate this exact deconstruct, solve, evaluate loop into your very next study session? How are you going to build your analytical depth? Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @theexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.
So before you click away to study, think about this final question. The next time you sit down in that exam hall and open a 9709 paper, are you just going to scribble down raw numbers like Alex and Sam, desperately hoping for the best, or are you going to step into the boardroom with confidence and pitch a flawless mathematical strategy they absolutely cannot ignore? The choice is entirely yours. Keep practicing, stick to the framework, and we will see you in the next explainer.